All right, continuing the Chapter 2A quick review. We're on lesson B4, which is electric potential and parallel plates. In this lesson, we're looking at a particular application of electric fields, and in this regard, parallel plates is the main application that we're going to be looking at. You may be familiar with another name for parallel plates or a specific type of parallel plate, and that's capacitors, which are used in electronics and your computers, your phones, all that sort of stuff. Okay. So in this section, and talking about parallel plates, we are going to introduce another concept in here, and that is the concept of potential difference, as you're probably familiar with it from Science 9, voltage. Okay, and we have this formula where it is change in energy over charge. Okay, now right off the bat, before we get into this in any more detail, you just have to be really careful with this formula because this E here does not represent electric field. Okay, energy is a scalar, and so you notice there's no vector arrow on the top. On your formula sheet, wherever you have electric fields, they will always have a vector arrow on top, and that's how you can differentiate between the two of them if you're really stuck on something and you're kind of in a little bit of a jumble or whatever and you can't remember which one is which. Remember that the vector arrow is always on the electric fields and energy doesn't. In essence, this formula here is the only energy formula that we have in this section. So whenever you're dealing with anything that involves energy, and that includes kinetic energy or something, an object or an electron moving with velocity, this is the formula that you're going to use. Okay? This formula is actually a formula for potential electrical potential energy, okay? And it's not V. V is potential difference, which, as you can see, is the amount of the change in energy per unit of charge. So V, or voltage, is not a unit of energy, okay? However, if we manipulate this formula and we have delta V times the charge, that is equal to change in energy. And this, in essence, is the electric potential energy. So in some resources and in some of the books or some of the workbooks and stuff that you might be looking at or online, you actually might see delta V times Q substituted in for your potential energy. So for example, if you were doing a total energy formula and you're finding the potential energy plus the kinetic energy, which we sometimes call mechanical energy in physics 20, right? You can see that this sometimes is written as delta V times Q, and this is 1/2 mv squared. Okay, so that's a really important thing to understand with this formula, is that delta V times Q is the electric potential energy, not V itself, but V times Q. Okay, so we're going to be using this formula quite a bit in parallel plates and in the remainder of this chapter and further on in Physics 30. It's a really important equation. It's also a conservation of energy type of question as well too, where like we see over here, we know that one type of energy is being converted into the other. And in particular, when we're talking about electric fields and parallel plates, we're going to be talking about this electric potential energy here, okay, being converted into kinetic energy. Okay, and all through this we've been talking about how the electric force and the electric field is very similar to the gravitational force and gravitational field. It's really similar in terms of electric potential energy to gravitational potential energy as well too, in terms of using an analogy and trying to understand what's going on. They're very, very similar, so it's very helpful for you to think of it that way. Okay. All right. So if I get back to this formula here, oops. We look at this formula here. We have joules for energy, and then we have coulombs for our charge. So delta V here, whoops, I realized I had messed that up. Delta V here is equal to joules per coulomb. We also know that that is a volt, right? Because voltage is measured in volts, okay? And as we're going to see in some of the examples that you do in your work booklet and that we went through in class, that this can also be written in other forms as well. Okay, if we expand joules and coulombs and that and break them down into their fundamental units. Okay, so fundamentally what we have here is an equation that's relating the amount of the change in energy from one location to another location for parallel plates. And I'm going to get into that part of it right now. Okay. When we have parallel plates, basically what we do is we have two pieces of metal, okay, and they're attached to some voltage source. So usually a battery or a variable voltage supply. So we have this one right here. So let's say that has 3 volts. So there's 3 volts across this, okay? Now the long end is the positive end, so that's going to make this plate positively charged, and this plate down here is going to be negatively charged, okay? Now this is empty space in between these 2 plates here, right? So there's a buildup of charge between them, and that's the essence of what a capacitor is. It's building up this charge between them. Now why this is so important and why we talk about this in physics and we use this so much is that the electric field that's produced in between here is uniform, okay? If we're drawing electric field lines, it's completely uniform between there, okay? Remember, we always draw electric field lines from the positive towards the negative. So if we drew that on here, our field lines are going to look like this. Okay? And if I'm drawing this perfectly, they'd be evenly spaced and everything, because the electric field in here is uniform. Okay, it's constant. It's not changing from one location to the other location. Okay. Now, if we go back to one of the formulas that we learned in the last lesson, we had electric field is equal to force divided by the charge. Okay. Now, if we know that the electric field is constant, and we're looking at say an electron or something of a constant charge there, if E is constant and Q is constant, then therefore the force that it's going to experience is constant as well too. So if we place an electron in here, it's going to experience a constant force all throughout the parallel plate. Okay, it's going to be a constant force. And again, that's exactly what we see when we talked in Physics 20 about the gravitational force. When we had an object of mass moving through the Earth's gravitational field, and assuming that that's constant at 9.81 meters per second squared, right, it experiences a constant force as well too. So there's a lot of similarities between these, and that allows us to do a lot of different calculations and do a lot of technological things with this as well. And that's why they're used, because the electric field is constant, it's steady, it's very reliable. Okay, outside of the electric or of the parallel plates, we basically say that the electric field is negligible. In Physics 30, we basically say that it's nothing. Okay, so we're only really looking at the electric field in between. Okay, now these parallel plates, okay, that we have in here, there is another formula that is going to describe the electric field between them. Okay, and the electric field between these parallel plates is a function of the voltage divided by the distance between the plates. Okay, I'll put a little e over top of this, or a little vector over there to be certain. Okay, so the electric field here is going to increase as the voltage increases, and it's also going to decrease as the distance increases. Pardon me. So if we spread these plates further and further apart, the electric field gets less and less. Okay. So this formula right here, this is really important to understand too on our formula sheet. This one is talking specifically about parallel plates. Okay. In reality, we can use it wherever there is a constant or uniform electric field. Okay. But for the examples that we use in our questions and that, the only place where we really experience that uniform electric field is when we're talking about parallel plates. So this formula should really only be used when you're talking about parallel plates. But any uniform electric field, you could use this formula as well. Okay, so I'm going to just flip over here now to, let me just see here. I'm going to flip over to my PhET simulation here. Let me just open this up. I thought I had it opened already. Oh, I do have it open down here. I'm sorry. Okay, so in this simulation, and by the way, you can, if you go to PhET, if you look up PhET online, okay, you can find these simulations. This one is called the capacitor lab. You see it at the top here. Oh, no, I messed that up. It's getting to be a little bit ridiculous. But I have the capacitor lab. You can see that at the top here, upper left-hand corner. You can look that up and you can play around with this. It's not a whole lot to do with this one. This particular simulation gets into a little bit more detail with dielectrics and multiple capacitors, which we don't deal with in Physics 30. But you can see it as just a visual demonstration of electric fields. Okay, so what I'm going to do here is we just have this battery here. So we have, let's say we have a 1.5 volt battery in here. And all that I really want to do is I want to just show you the electric field at how it changes depending on the voltage and the distance between them. Okay, so if we start at 0 volts here, okay, we can see that there is no electric field in between them. Okay, as we increase the voltage in here, you can see that the electric field gets larger and larger. And again, we expect that through our formula here. E is equal to V over D. As V goes up, so does the electric field. Okay, so I'm going to just bring this down a little bit so we can see the lines a little bit better in here. Okay, so we have an electric field of 45 volts per meter there at this point. So I'm going to leave the voltage constant now, and what I'm going to do is I'm going to take a look at this distance between them. Okay, so based on this formula, if I move the distance further apart, the electric field should get smaller, and if I move it closer together, it should get larger. So that's what I'm going to do here, this separation here. If I move it closer together, we can see over here now, again, that my electric field is getting larger and larger, and if I move them apart, you can see it's getting less and less and less. Okay, that's the greatest distance that they let me fool around with that on here. Okay, so just a visual for you again in terms of seeing the electric field, how it changes depending on the voltage between them and the distance apart. Okay. Now keep in mind, and we talked about this in class quite a bit, and we did a little lab with the saltwater solution and the rulers, and then obviously we had the voltmeter. But keep in mind too that voltage is a function of location, right? So when we talk about this in here, the voltage across the two parallel plates, that's the distance between the plates. But if we have an object, and maybe I'm just going to decrease or turn off these field lines for a second here. If we have a negatively charged object, let's say that it's really close to the plate here, okay, the voltage that it's going to experience is going to be very, very large. Because if we let this go freely, it's going to move up towards this plate here, right? So if it's right at the plate, it's going to have the voltage the complete voltage between the plates. However, if this negative charge is right on the positive plate, the voltage that it's going to experience is basically going to be 0, okay? If it's halfway in between, this negative charge was halfway in between the positive and the negative, then it's going to have half the entire voltage, okay? And this is a really important concept. It's important in parallel plates, but it's important in talking about voltage in general, okay? So that's just a little bit about the parallel plates formula and how parallel plates work as well too. So in your workbook then, there's a series of questions, and we went through these in class before we were let out about parallel plates and these formulas. And so again, as I've mentioned before, if you can review that assignment and make sure that if you have any questions about parallel plates, voltage, that sort of thing, to make sure to ask me. The only other thing that was in this lesson as well too was the current formula. Current is equal to charge divided by time, which is not a really large concept, but essentially current is a rate, right? The rate at which charge passes a point per unit of time, right? So we take our total charge in coulombs divided by time, and that gives us our current in amps. So you might see some questions talking about that a little bit as well too. Usually, if you get these questions, they're trying to get you to tease out Q from this, and then maybe you're using Q for something else in the question. in some of the formula.